Okay, in this doodlecast we're going to present the definitions of the mass flux, and these definitions will be used throughout the course, so it's important that we understand them and also that these are definitions. So we'll begin with our system consisting of A molecules, which I'll denote by closed circles. And then we'll put in some B molecules here, which will have open circles. And so we'll have a binary system, but all the definitions that will be presented are applicable to multi-component systems, and you'll see how easy that is to extend the binary representation. Okay, so here's our plane that's located perpendicular to the x direction, and we'll simply count these A molecules as they cross the plane over some differential period of time, delta t, and each molecule that crosses will record its velocity. So we'll let ma be the mass of any eighth molecule in the system, and we'll denote that particular molecule by a subscript Ka. And the definition of the mass flux in a stationary or lab frame, which we'll draw over here, NaX will simply be the sum of those molecules as they cross the plane, their mass times their velocity, VKAX. And the definition requires that we divide by the volume occupied by those eighth molecules that cross the plane. So we'll denote that by delta epsilon. That's the volume occupied by the A molecules that cross the plane. Okay, so we've rewritten the definition on a fresh page, and let's look at the units here. The first term has units of volume, so that's 1 over length cubed. The next term has units of mass of A. And the velocity, of course, has units of length over time. So the net result then is mass of A divided by length squared, which is an area, times time. So those are the units of the mass flux of A in the lab frame. And the lab frame is a stationary frame, a fixed frame. Okay, so our next definition is the species average velocity of A. So that is defined as simply VAX, a number average. So that you count those molecules again that are across the plane, and let's say that number is NKA, and you simply take a numerical average of each of the velocities. And that is defined then as the species average velocity, in this case of component A. Now we can use that species average velocity in our definition of the mass flux, because the mass of A in this definition is the mass of a molecule of A, and that's a constant and can be taken outside of the summation sign. So we can use then this definition to replace the remaining summation of those Ka molecules that we've recorded their velocities. Okay, so doing that is very simple. NaX would be equal to the mass of A, which is the constant factor we take outside of the summation sign. And then for the summation, that gets replaced by the number of molecules that we counted times the species average velocity of A in the x direction. So looking at this grouping of terms, you notice we have the mass of a molecule of A, Ma, times the number of molecules that crossed, divided by the volume occupied by those molecules. So that indeed is the mass concentration of A in the system, which we denote as rho A. So this is the mass, total mass of A per unit volume. So again, we have a mass flux related now to the species average velocity in the mass concentration of A. And it's important to note that flux is a vector quantity. That means we have to specify both the magnitude and the direction. So in general, using the tilde as a vector symbol, the mass flux as a vector quantity, Na, would have an x component times a unit vector in the x direction plus a y component times a unit vector in the y direction plus a z component times a unit vector in the z direction. Okay, the next definition is the mass average velocity. So this quantity is defined as a velocity which is a weighted average according to the mass concentrations of the species that are present. So it would be rho A times the velocity in the eighth direction plus rho B times the velocity in the b direction. And rho here is the total mass density of the mixture, which is defined as rho A plus rho B. So that's the total mass over volume. And that's the mass density that we're used to seeing in multi-component thermodynamics. And rho A and rho B are simply the mass concentration of A and mass concentration of B in the system. So this is then the definition of the mass average velocity of a mixture. Now we define a mass flux of A relative to that mass average velocity. So that will denote by lowercase j sub A. And lowercase j sub A is defined as the flux of A relative to that mass average velocity. So we subtract out from the species average velocity the mass average velocity of the system. And so that, you can see, is equal to rho A times VA minus rho times V. And we know then that rho A VA by definition is the mass flux in the lab frame. And therefore we have a very important definition between the relative mass flux JA and the mass flux in the lab frame NA, and the difference being this factor rho V, where rho is the species mixture density and V is the mass average velocity of the mixture. And this is a very important relationship that we will be using all the time in this course. A relative mass flux, lab frame mass flux, and mass average velocity and species concentration.